for the invitation. I think I'm the 4th time here, and it's already a great pleasure to be here. It's a great place. So my lectures will be mainly about syzygies. And first question, what is a syzygy? So if you Google it, then you might find different results. So Wikipedia may ask you what you actually meant by your search. So Wikipedia produces one result in poetry. So in poetry is a combination of two metrical feet into one single unit. There is one concept in philosophy which is due to Vladimir Solovyov, which is called syzygy. There is one syzygy in fiction. There was an episode of X-Files, for those of you who watched the series. There is a Japanese band called Syzygy. In business, there is an IT company from Silicon Valley. In biology, means a pairing of chromosomes. So for them, it seems to be an important notion as well. So in astronomy, it's a straight line configuration of 3 celestial bodies. And finally, in mathematics, it's a relation between the generators of a module. So we will be mainly concerned with the mathematical term of syzygy rather than with the others. So let's discuss a little bit of history of syzygies. Following the introduction of homogeneous coordinates by Plücker in 1830, people became interested in geometric properties of plane curves. So they were studying properties. They were interested in studying properties of plane curves that were invariant under certain classes of transformations, and they soon realized that this invariance actually means the invariance under the action of a group. And there was a problem related to these questions. So if in modern language, if we have G an algebraic group acting on a projective space Pn, so this induces an action on the polynomial ring. Then describe the invariant polynomials. Under this action. So that's so this is one problem which is related to the classical invariant theory, and if we denote by Sg the invariant polynomials, they form a subring, of course, in the ring of polynomials. And there is a famous problem raised by, or question raised by David Hilbert. It's known as Hilbert's 14th problem, 1900. So is this Sg finitely generated as K algebra? So that's this problem is one of the 23 famous problems from Hilbert's list. However, he presented his problems separately. So there was a first list of 10 problems he presented on August 8, 1900 at the ICM Congress in Paris. It was a very sunny morning. And later on, he completed this list up to 23. Apparently, there were 24, but he erased one of them. So this problem was not on the initial 10 problem list. So it came earlier. Later. And then I think that the English translation of this famous list was done 2 years later in a paper in the Bulletin of the American Mathematical Society, containing the full list of problems. Okay, so the answer is was given by Nagata, and the answer is no. However, if G is special, like a linear reductive, then the answer is yes. So linear reductive means that whenever you have an action of G on two vector spaces and an epimorphism between these two vector spaces, then what it's induced at the invariant level is also an epimorphism. So for example, finite groups satisfy this property. Hilbert gave a proof. Hilbert proves it in 1899, I guess, for a G finite. Okay, so that was one question which was raised. And then another question raised by Hilbert is that the following. So suppose we manage to prove the finiteness of finite generatedness of the ring of invariants. Then how many independent homogeneous polynomials invariant under the action of G are in each degree? And now the solution found by Hilbert, the answer was very beautiful. So he found the following answer. So if we look at the function that associates to any d the dimension over k of SGD, so these are homogeneous polynomials in degree d, which are invariant under the action of G. Then for d large enough, this function is polynomial. So I think it was the same paper, if I'm not mistaken. Anyway, it was a very surprising and very unsatisfactory answer for that time, because, for example, when so people were very interested in, as I mentioned, in classical invariant theory, and the big star of the invariant theory at that time was Gordon. And Gordon, when he saw this statement and the proof, he said that this is not mathematics, this is theology, because for them mathematics was, I mean, whenever you wanted to give something, you should give an explicit formula, and people wanted very concrete things at that time. So the way of thinking was completely different. Okay, So this function behaves asymptotically like a polynomial. Nowadays, it's what we call the Hilbert polynomial, and this generalizes to modules. So let's begin now our discussion. So let me fix the setup. So throughout the lectures, I will fix an algebraically closed field of characteristic 0. And my favorite example is the complex numbers. And we take the polynomial algebra. We fix V to be the span over K of the variables. So these are linear forms. And M, a finitely generated graded S module. So we want to understand this module, and Hilbert, in the same paper, suggested that, of course, he didn't have the notion of a module at that time. Even the notion of an ideal was not clear. The ideals, as we know them, were introduced by Emmy Noether much later. But basically, roughly speaking, one of his brilliant ideas was that he noticed that when we work with, unlike classical linear algebra, when we work with modules over rings, it might happen that we have modules which have no basis. So there are modules which are not free in modern terms. So he knew this phenomenon, and he said, okay, if we want to find a sort of basis in a module, what can I do? I can approximate this module with a free module, and then to see what happens with the generators, whether they are linear, whether they are independent or not. And that's how the minimal resolutions and syzygies appear. So we try to approximate M with a free S module. So we just choose a bunch of generators, and these generators will have some degrees, and then this means that we have something like a direct sum S of minus di to M. So this means just S, but we shift the degrees by di, so that if we map the canonical basis here to the generators of the module, this map will be of degree 0. So this is surjective. And we look at, let's call this F0, and we look at K0, which is the kernel. So it might happen, so a phenomenon, which is typical when we work with variable scalars, like over rings, phenomenon. So in general, K0 is not free. Well, if we worked with vector spaces over a field, then of course any subvector space of a vector space is free. But this is not the case in general. And then he repeats the argument. So, but however, K0 is finitely generated. And that's another beautiful result, which we know today as the Hilbert basis theorem. And since this is finitely generated, we can start all over again. So take generators. of K0 approximate K0 by a free module, and so on. So we can iterate this this process, and of course we would like this process to be finite, and that's another theorem of Hilbert, which we know today as the Hilbert-Syzygies theorem. If we choose a finite number, a minimal number of generators at each step, then the process is finite. Meaning that after a number of steps, which is n plus 2 steps, if we start from 0, if we start counting from 0, the kernel will, n plus 1, the kernel will be free, so we have to stop. And that's how minimal resolutions appear. So a minimal resolution, let me give the definition. A minimal graded resolution of M is an exact sequence. And let me write the exact sequences in a very funny way. So I will write the arrows from the right to the left. That's the Macaulay convention, which I'm not used with, but I'm trying to get familiar with. So if during the lectures I will switch, please please tell me. So we get M, F0, F1, and so on, where Fi's are free graded S modules. The differentials are of degree 0. At each step, and so this is minimal graded free. Sorry, I forgot the word free. So that's free resolution. This is graded resolution. And now what does minimal mean? So minimal can have 3 meanings, which are equivalent. So either when twisting by K over S, where K is S mod by the irrelevant ideal, all the differentials are 0. So we kill the differentials if we mod out the variables, or, which is the same thing, so these being free modules, the maps are given by matrices. This condition is equivalent to saying that the elements of the induced matrices are either of degree bigger than 1 or 0. So there are no constant entries in all these matrices. No constant non-zero entries in these matrices. Or the third equivalent condition for minimality is that at each step we choose a minimal number of generators for the kernel of the differential. And from Hilbert-Syzygies theorem, this implies that the resolution is finite. More precisely, it will end at fn plus 1. Or before, if we are lucky. Okay, and this let me fix some notation.
Why does the symbol of the resolution is finite?
No, that's the theorem. That's Hilbert's.
Well, I thought it was, you were claiming it followed from.
No. It follows from Hilbert. We will actually see a proof of this fact. We will see a proof of the finiteness. Okay. So if these FIs are free and graded, then we can define some numbers which are here. So if I will be a direct sum of a number of copies of S, but with the degrees shifted because we want these differentials to be of degree 0, minus j, beta ij. So we collect, if we have several copies of S of minus j, we collect them together, and we mark this multiplicity here. So that's over j. So these beta ij are called the so beta ij. So we get a bunch of numbers. Beta ij are called the graded Betti numbers of M. So why are they unique? Because the resolution, the minimal resolution, so that's a fact, minimal resolution or minimal resolutions are all isomorphic. So maybe the minimal resolution itself is not unique, but it's unique up to some automorphisms of the factors. So the factors are unique. So maybe the matrices are not unique because we can choose different bases, but then we get isomorphic resolutions. So in particular, these FIs are unique. So these numbers are unique, and they only depend on so beta ij only depend on M. Okay, and let me add some further notation. So Kij will be beta I plus j. For the moment, it's a very obscure notation, but it will come in the course of the lecture. So now we can collect all these numbers. So we get what have we done so far? we start with a finitely generated graded module over the ring of polynomials, and we get a bunch of numbers which are indexed by two numbers, I and j. So the first impulse will be to collect them in a table, to put them in a table. And that's what we do. That's how we get the Betty table of M. It's just that we collect all these numbers, but instead of writing the number beta ij at the intersection of I and j, we will write it in a very funny way. So the Betty number would look like this. So here I have I, here I have j. We will start with beta 0 I, beta 0 I plus 1, beta 0 I plus 2, and so on. Now I write from left to right. So I start with 0. So these are the numbers corresponding. Well, I should have written probably k. So this I here is the j here for I equals 0. I hope that's not too confusing. So let me switch to k. So this is k, beta k, k plus 1, k plus 2. Okay, and now next to beta 0k, instead of writing beta 1k as we would like to, we will write beta 1 k plus 1. And then we continue with beta 1 k plus 2 and so on. Here we write beta 1 k plus 2. Then beta, sorry, this is beta 1, this is beta 2, sorry. That's beta 2 k plus 3. Here we have beta 1 k plus 3, beta 2 k plus 4, and so on. So actually, at the intersection of now I got it all wrong. So that's the k, yeah, yeah. So this should be j and this should be k. Okay. Anyway, the moral is that what's at the intersection of k and j, we write beta j k plus j instead of beta j k, as we would like to. And there is some reason for doing that, and I will try to give you the reason. So there are several reasons actually, but one of them is the following. So let's so the explanation for this term, this notation. So let's assume that X was a variety in Pn. That will be anyway one of the favorite examples. And M was the homogeneous ideal of X. So how is the minimal resolution constructed? So we start with Ix. Then we get here the F0, which is direct sum of S of minus j beta 0 j. Then we have F1, which will be the direct sum of S of minus j beta 1 j, and so on. So let's focus a little bit on this map. So the first map will be given by the generators of the ideal. So to get the first map, we need, so the first map gives the generators. of the ideal. Meaning that we take a minimal set of generators of the ideal. These will have some degrees. We collect together those generators that have the same degree, and we read them here in this map. So that's simply the map given by, say, P1, PM, where these are the generators of the ideal. How do we get the second map? So for the second map, we said that we take the kernel. So taking what is an element of the kernel? An element in the kernel is simply a relation between these generators, right? So now we have to identify the relations between these generators, and these relations will have some degrees. And then we identify the degrees, and we map. We take the corresponding map. But now, why do we order? So, in this example, the beta 0 case will take care of these degrees. So, in this example, the first column will read the degrees of the generators. So we have beta 0k generators in degree k, beta 0k plus 1 generators in degree k plus 1, and so on. So far so good. What about this column? Well, this column takes care of the relations among the generators. But if we look very carefully to these relations, we see that on each row we read the linear relations. So in this row here, every time we have a horizontal arrow, we have a linear relation. Linear relations are relations with the lowest possible degree, right? We cannot have lower than linear. So it's somehow very natural to put them, to read them on a row of the table. What we have on a vertical diagonal, we have quadratic relations. And here we have cubic relations, and so on. So that's the meaning we write the table as it is. Because if we wrote it in a classical way, then the linear relations would have been on the diagonal, which is very unnatural. So if it's linear relations, then they should be on a line, right? On a horizontal line. So that's the meaning of this convention. That's why we write things like this. Okay. And now, oops, should speed up a little bit. These graded Betti numbers, so beta ij, will give right away a formula for the Hilbert function. Of M. Because if we look at this, or here, if we look at the minimal resolution, then this is exact. So if we want to compute the dimension of any graded piece of M, then we have to look at every graded piece of this exact sequence. So we just have to count polynomials, not more than that. So that's how, from the existence of minimal resolution, we also get a formula for the Hilbert function, which is, I'm going to write it, hm of n will be, so this is by definition the dimension of mn, is the sum over I and j minus 1 to the I, beta ij, n plus n minus j, choose n. And of course, for high enough n, these will all be polynomials. So that's why the Hilbert function is actually polynomial. And some notation. So if we denote by beta j to be, so we collect these coefficients over j over I minus 1 to the I beta ij, then the Hilbert function will have a simpler formula, is the sum of bj n plus n minus j, choose n. What is this number? So if we look at the Betti table, this number is the alternate sum on these diagonals of the numbers that appear on these diagonals. For example, bk plus 2 will be beta 0 k plus 2 minus beta 1 k plus 2 plus beta 2 k plus 2 and so on. It might continue. So that's the alternate. We look at the diagonals and we take the alternate sums. So that's what it is. And not only that, so the Hilbert function can be reconstructed from these capital B's, but also capital B's can be reconstructed from, can be recovered from the Hilbert function. Because, for example, if we take the maximal n, here n equals j, or j equals n, so that's for j. If we take j equals n, then this will be 1, and then we get bn equals hm of n minus the sum of the others. So we also get a formula that bn is hm, let me see, hm of n minus the sum over k lower than n, should be like that, of bk n plus n minus k, choose n. So let's see, what do we have so far? We have this bunch of numbers, which are the graded Betti numbers. The Hilbert function can be recovered from these graded Betti numbers by this formula. If we take the alternate sums of these graded Betti numbers on the diagonals, then we get a nicer formula for the Hilbert function. But also, these sums can be obtained from the Hilbert function. So to give, the moral is that to know hm is the same as to know this bk.
The values of the Hilbert function have some obvious geometric meaning.
Of course, yes.
Geometric meaning of these capital B's, or are they just a tool?
No, so since they are equivalent, the geometric meaning is the same.
No, the individual hm of n's.
I see.
Is the space of functions of
course.
variety.
Yeah. Yes, yeah. Well, it's this formula. So somehow.
So just in terms of a purely geometric statement, is there any kind of geometric statement that tells you what the BNs are?
We have to pass through the Hilbert function if we want to find the geometric meaning of the BNs. Yeah, so I don't know.
So So just for the moment, convenient bookkeeping.
Yes, yeah.
Okay.
It's just that this, so to give sorry, this is an n missing. To give the Hilbert function is the same as giving these numbers. So it's equivalent. But these numbers are obtained from the graded Betti numbers. So, so the graded Betti numbers, if we know the graded Betti numbers, then we know HM. But is the converse true? So if we know HM, is it true that we know the graded Betti numbers? So the answer is no. And here's one example. So we take X in P2, a bunch of 4 distinct points. And if there are 2 possibilities, well, there are 3 possibilities actually, but we will only analyze 2 because these are relevant for the question. So if X are general, so the first case, so if there are general points, then 4 general points in P2 are the intersection of 2 conics. And these 2 conics will have only one relation between them. So we have Q1, Q2, whose common zero set is X. And the only relation will be Q2 times Q1 minus Q1 times Q2 equals 0. So that will give us the, if we write carefully, the graded Betti table of the ideal of X. So we have 2 conics. We have no cubic and no quartic and so on. Well, of course, we have cubics and quartics, but they are all generated by these conics. But we need no extra cubic or quartic. And then we have one. We said that the quadratic relations we write on the diagonal. So there are no linear relations, so there is nothing on this row, but we have one here. And this is it. So this is the graded, that's the Betti table. And the Hilbert function is the following. So 0, 1, 2, 3. So that will be NHX. That's 1, 3, 4, 4, and so on. So this is the Hilbert function. Because they all, yeah. Okay. And now the second case, which is very similar to this one. So the second case is when 3 points are on a line and 1 is off. Then to generate the ideal, we need we need 2 quadrics and 1 cubic. So the ideal will be generated by Q1, Q2, and 1 cubic. And we can write explicitly the relations between these generators.
Wait, where is this? The 3 is, oh, because it's 3-dimensional vector space.
Yeah, it's 3-dimensional vector space, right? Yeah. Okay. And so we need this cubic because we have 3 points on a line, and we need the cubic to cut these 3 points. Okay, and if we write the Betti table, so we have the 2 conics, the 1 cubic here. And if we analyze, we can write explicitly in coordinates everything. We find one linear relation between these conics and one relation which is quadratic in these conics and linear in the cubic. So that's the Betti table. And the Hilbert function is the same. Is the same. Yeah, because the fourth point is here, so that okay because the 4 points are not on the line. But so we see that the Hilbert functions are the same, the Betti tables are different. But on the other hand, if we take the alternate sum on this diagonal, we get 1 minus 1, which is the same as 0 minus 0. So the alternating sums are the same. On each diagonal, the alternating sums of this table, that table over there, and this table are the same. That's somehow an illustration of what I have written down here. Good. And let me give one example, and then I will. I'm afraid I will have to stop. So the favorite examples will come from geometry. Favorite examples are when M comes from geometry. I will say more about it tomorrow. But I will give at the end of today's lecture one particularly interesting and important example, which is for M, the residual field. Then we can write, let's try to find a minimal resolution for that. So we have here the residual field. It will have one generator, so we will put S here. The generator is in degree 0 because it's 1 is mapped to 1. Then the kernel is generated by x0, xn. Right? So we have n generators in degree 1. So here we have a direct sum, or n plus 1 copies of S of minus 1. And the map is given just by multiplication by x0, xn. So now what's the kernel? What should we put here? So let me write this in another way, because we have learned actually the language of tensors from the very nice lectures of Professor Landsberg before. So I'm going to use the language of tensors. Let me write this in another way. So I will write it as V tensor over K with S of minus 1. So it's about the same thing. So the question is now, how do we continue? So what are the relations? So we can find right away some relations, which are the trivial relations, like xi xj minus xj xi equals 0. And these relations will give a tensor xi tensor xj minus xj tensor xi in V tensor V, which when we multiply the elements here will map to 0. But this we have seen in yesterday lectures, or the day before yesterday's lectures of Professor Landsberg, that this is an alternate tensor. So this comes from a wedge. So that comes from wedge 2. So this comes from wedge 2. And in fact, we can continue. So the map we are looking for is the following. So we have V tensor S of minus 1. We should put something here. And this thing is exactly wedge 2 of V tensor S of minus 2. And what is this map? So the map, we can write it in the following way. So if we are given xi wedge xj tensor sum polynomial, this will be mapped to xj tensor xip minus xi tensor xjp. So this is the map. It increases the degree by 1. That's why there is this shift. And it's defined in this way. This might look a little unnatural, but let's write down a very simple example for the case n equals 2, to convince ourselves that this is exactly that's the right thing to do. So if we consider the case n equals 2, we have three variables, x1, x0, x1, x2. And then we can find a matrix which multiplied by this vector is 0, which is the following matrix. So x0, x1, x2. If I multiply by 0, let's see, minus x2, x1, then x2, 0, minus x0, minus x1, x0, 0, this will be 0. And also this matrix multiplied by, let's call this A multiplied by the vector x0, x1, x2, this is 0 again. So we find we have a matrix of relations, but this matrix is antisymmetric from what we see. And being antisymmetric gives an element of wedge 2, because it defines an antisymmetric bilinear map, right? And this matrix actually, and then I will finish this matrix. So the matrix from wedge 2 to V tensor V, 0. So the matrix given by x wedge y is mapped to x tensor y minus y tensor x. In this case, is represented by so this map is represented by the matrix 0 minus x2 x1 x2 0 x0 minus x1 x0 0. Well, in the following sense, that whenever we have a tensor in A times B times C, which gives a map, as we have seen, from A dual to B tensor C, choosing basis in A and B, this map can be seen as a matrix with entries in C. So that's what it is. That's where the second V comes from. So the first V stands for a map from wedge 2 of V tensor V with entries in V, and this is that's what it is. And now we can continue, and this is the Koszul complex. So the full minimal resolution of the residual field is 0k s v tensor s of minus 1 wedge 2 v tensor s of minus 2. Then it continues with wedge 3 and so on up to wedge n plus 1 v tensor s of minus n minus 1. And that's a minimal resolution. And in coordinates, the map from wedge p plus 1 of v tensor s minus p minus 1 to wedge p of v tensor s of minus p is given by xi0 xip tensor some polynomial p is mapped to the alternating sum minus 1 to the j to the I or j, let's call it j, xi0 wedge. We remove what's on the jth position, xip, and then we multiply this element by ip. Okay, and I think I will stop here for today. Thank you very much.